How's lights down? All right. Okay, so here it is. This is Mars, the object of our affections. It's a truly terrible place. If you went there, you would hate it. The average temperature is about 60 degrees below 0 centigrade. If you took all the water vapor in the Martian atmosphere and you condensed it out on the surface, you would make a layer of frost that's barely 1/100 of a millimeter thick. So it's a cold and dry and desolate world today. But there are intriguing hints that in the past it may have been rather different. This is a picture taken from orbit by a spacecraft called Mars Global Surveyor. It shows a valley snaking across the Martian surface. This valley is only about 1/2 kilometer wide, so it's a little thing. And if you look carefully, you can actually see the channel through which the water that carved that valley flowed. You can't do this on Mars today. On Mars today, it's too cold, it's too dry, this can't happen. So what this is telling us is that in the past, Mars was in some sense different from Mars of today. It was warmer, it was wetter, and hence it was more like Earth. And because it was more like Earth, it would have in the past potentially have been a place that was more suitable for life. Now, any geologist will tell you that if you have erosion, then somewhere else you have to have deposition. And there are places on Mars where you can go and you can find these wonderful deposits of layered sedimentary rock. Now, a geologist will also tell you that one of the great things about layered sedimentary rock is that it can, in its details, preserve evidence of what conditions were like when those sediments were laid down. And by looking at the chemistry, the mineralogy, the texture of layered sedimentary rocks, you can learn a great deal, if you have the right equipment with you, about what the conditions were like at the time that those rocks were deposited. So our job was to build 2 robotic field geologists and send them off to Mars. This picture was taken at Cape Canaveral in Florida just about exactly 5 years ago. Shows the Spirit rover in the foreground here, all tricked out and ready to go to Mars. That's Opportunity in the background, doesn't have her wheels on yet. I'm the good-looking guy in the white suit here. These rovers were designed to go to 2 places on the Martian surface, to look for clues in the rocks, to last for 90 days, and to drive 600 meters over their lifetimes. Today is day 1,526 of our 90-day mission to Mars. And both vehicles continue to do well. The scientific payload on these rovers comes in 2 parts. The first part is supported by this big, fat, white stovepipe of a mast here. I'm noticing the projection, the image is too wide, and we're getting cut off on both the right and left sides. If there's any way that anybody who knows how to work that projector can adjust that, I would appreciate that, because some stuff is going to get cut off. Anyway, the one part is supported by this big stovepipe of a mast here, and it supports 2 instruments. One is some cameras at the top, high-resolution color stereo, and they give us a nice view of the terrain around us. And then there's an infrared spectrometer, and it lives down inside the rover where it's mechanically and thermally stable. It's nice and warm in there. And this thing looks up that mast, which is hollow on the inside, and then there's a pair of mirrors at the top, and it uses those mirrors to scan the terrain around the rover, getting the same view of the countryside that the cameras get. Then on the front of the vehicle, there's an arm. The arm has a shoulder, an elbow, and a wrist. It's exactly the same dimensions as my arm. That is purely a coincidence. And on the end of the arm, there's a hand, and the hand has 4 fingers. There's a microscope. There are 2 more spectrometers to tell us in detail what the rocks are made of. And then there's a device that we call the RAT, R-A-T, the rock abrasion tool. And the RAT is a diamond-tip grinding tool for grinding into a rock, stripping away the outer layers of the rock and sort of opening a window into the rock's interior that we can look into. The spacecraft that gets the rovers there is built sort of like one of those Russian doll sets, where there's a doll inside a doll inside a doll. Okay? The rover right here folds up in a horrifyingly intricate fashion to make this compact little package. And it is then encased within the lander. The lander is shown here, and the lander has 3, we call them petals. One here, one here. They're like the petals of a flower in that they fold up around the rover, encasing it, protecting it. And so when the lander's all folded up, it makes this kind of tetrahedral pyramid shape. That is then, in turn, encased in another shell that consists of two parts. One right here is the heat shield, and that protects the vehicle during its fiery descent through the Martian atmosphere. And then there's this cone-shaped thing that we call the back shell that goes on the back of it. So here's the spacecraft all put together. And then this kind of blue frisbee-looking deal on the back end, that is what we call the cruise stage. And the cruise stage provides propulsion, it provides electrical power, it provides the things that you need to get you to Mars. This is what the spacecraft looks like when it's all put together. This is in a big thermal vacuum test chamber at the Jet Propulsion Laboratory in California, where we built the vehicles. We launched in the summer of 2003 on 2 Delta II rockets from Cape Canaveral in Florida. It took us 7 months to get to Mars. When you hit the top of the Martian atmosphere after 7 months in space, you're going Mach 25. 25 times the speed of sound. And the vehicle uses the heat shield to bleed off that velocity, to bleed off that kinetic energy, and to slow down. Once you have slowed down to just a leisurely Mach 2, you throw out a supersonic parachute. We discovered that supersonic parachutes were rather difficult things to design and build. The lander descends on a long cord called a bridle, and this is the configuration that the vehicle is in as it is still screaming down towards the Martian surface at about 200 or 300 miles an hour. You don't drift down lazily on a parachute on Mars. The atmosphere is too thin. We had a terrible time with our parachutes. These are some tests that we did of a parachute. This is the parachute design that we thought was going to land us successfully on Mars. And we did these tests at a National Guard gunnery range outside of Boise, Idaho. It's the kind of place where you can drop big, heavy things from the sky and they won't kill anybody. And we dropped this test article from a helicopter at 4,000 feet. It fell towards the surface, deployed the parachute. The parachute blossomed and made this beautiful orange and white bowl, and then it just exploded, just ripped to ribbons. And parachute test after parachute test failed. What had happened is that as we added details to the design of our rover, we came to realize that it had grown in our estimate of its mass. It had gotten heavier, and it got heavy enough that the parachute simply could not handle it. We did not have our first successful parachute test until 8 months before we had to be on top of the rocket in Florida. It was terrifying. This is a picture from that test conducted in a big wind tunnel that NASA maintains in Northern California. Then there are the airbags. What? That's an engineer at JPL being consumed by his work. The airbags are like the airbags in your car, except way more expensive. And what they do is they inflate explosively around the vehicle about 10 seconds before impact with the surface. About 3 seconds before impact, we fire some rocket motors. That zeroes out the velocity in midair. We drop the airbags. They fall to the surface, and they bounce. And they bounce, and they bounce, and they bounce, and they roll, and they roll, and they roll. And they can bounce and roll as much as a kilometer or so before they finally come to rest. We had a tough time with our airbags as well. This is pictures from our first airbag test, and you can sort of get a sense from the looks on the faces that it's not going real well. We did these tests at the world's largest vacuum chamber maintained by NASA outside of Sandusky, Ohio. And what you do is you pump the chamber down, and then you use giant bungee cords to send the airbags smashing down onto a platform that's studded with sharp, nasty rocks. Each rock had a name. This one here is named Snaggletooth. And those rocks had a nasty way of ripping up our airbags. And you can see the bags shredding. There's a gaping hole in one. Again, the vehicle had become too heavy. We finally did solve the airbag problems too. The picture up here shows one of our successful airbag tests. And then, of course, the ultimate test, these are airbag bounce marks on the surface of Mars. Now, once the vehicle is on the surface, you retract the airbags. The lander flips itself upright by opening the pedals in the appropriate order. And then there inside, all folded up, is our little rover. Doesn't look like a rover yet. What it now has to do is origami in reverse unfolding itself through these multiple steps. There were a lot of parts of this mission that scared me, but this is one of the parts that scared me the most. There are so many gears and motors and springs and hinges and latches that have to work perfectly. These are the life-giving solar arrays. Those are the solar cells that produce the power that charges the battery at night. And if those don't deploy the first day on Mars, we don't survive the first night on Mars. The camera mast comes up, the antenna comes out, and now the vehicle is in a safe configuration. The sun is shining on the arrays. It's still not ready to go anywhere yet because it still has to stand up. Now watch this. This is worse. There's a jack that lifts it up like a jack in your car, and then watch what the front wheels do. Watch this. Yeah, I still get the heebie-jeebies when I watch that. I mean, you know, if those latches don't latch, you're done. It's all over. But it all worked. Now, we initially thought, when we came up with this whole cockamamie scheme of bouncing and unfolding and all of that, that once we got to this point here, once we got to the stage where the rover was standing up, everything was deployed, we were kind of home free. All we had to do was cut the big cable that ties the rover to the lander and go monster trucking down onto the Martian surface, and everything would be good. And we did some tests. Yeah, this was a bad day. It turns out that when you drive one of these rovers off of a lander, it can flip itself upside down, and that's not a good thing. So what we had to do was invent some ramps. If you saw these in the little video clip that I showed you, there are these fabric ramps that stow between the pedals, and then as the pedals fold out, the ramp snaps into place. There it is right there. It's made of the same fabric that the airbags are made of. Once you get off of the lander, you've got to deal with the fact that the Martian surface is not exactly paved. Okay, it's got rocks, it's got bumps, it's got crevices, it's got all kinds of topography that the rover has to be able to negotiate. And so our mechanical engineers had to invent this incredibly clever system that allows the 6 wheels of the vehicle to go up and to go down and to conform to the topography that they encounter. Watch how this works. Check this out. Just watch the wheels. Watch how the wheels move as it goes over the terrain. I mean, if we find a corrugated metal roof on Mars, we're all set. But watch, it's going to spin here. It really is a remarkable system. Works extraordinarily well. Then there's the issue of how to control these things. Now, of course, what I wish I had is a joystick, right? What I want to do is I want to sit in my office and steer the thing around rocks. But you can't do that. Even on the night we landed, when Mars and Earth were pretty close together, it took 10 minutes for a radio signal traveling at the speed of light to go from Earth to Mars. Something happens on Mars, radio signal comes back, 20-minute round trip time, I ran into a rock. Okay, so you can't joystick it. What we've had to do instead is to endow the vehicles with vision and intelligence and the ability to make their own decisions about what is safe and what is not. Each of the rovers has a pair of these kind of googly-eyed cameras on the front bumper and on the back bumper. And they take these wide-angle fisheye pictures. And what the rover does is it looks at those pictures, develops a three-dimensional model of the stuff in front of it, and it can make its own decisions about when it's safe to drive over and when it's so dangerous that it has to go around. And we can actually program different levels of courage or cowardice into the vehicle, depending on how dangerous we think the terrain might be. Here's an actual drive that was done by the rover Spirit. This we commanded, and now it's making its own decisions from here on out. So it's driving along, and right here, there's a scary pile of rocks. So the rover sees it, thinks about it, doesn't know what to do for a minute, doesn't know what to do, says, okay, I know what to do. I'm going to do this backwards. It makes that, it makes that beep, beep, beep sound when it backs up. Pile of rocks here, thinking about it, says, okay, let's see, I'll go this way. They told me to stop right here. All done. They're pretty smart little machines. Okay, the RAT, the rock abrasion tool. This is one of the most important things on the rover. When a rock sits on the surface of a planet for some period of time, it gets exposed to the elements. It gets exposed to sunlight, wind, humidity, dust, things that can change the outer layers of the rock. What we're doing is we're looking for clues, sort of like a detective at the scene of a crime. And those clues are contained within the unaltered rock. But if the outer layer of a rock has been altered, then you've destroyed the evidence. And so what you want to do is get into the rock and drill away through the altered stuff into fresh rock underneath. So the rat is a diamond-tipped grinding wheel. And this grind head here is made of diamond. It spins at 3,000 RPM. And this thing is able to grind its way into solid Martian bedrock. Now, the rat is effectively a power tool. It's the world's first interplanetary power tool. And as with all power tools, you have to be very careful when you operate them. Because you don't want that to happen. I'm sorry, I couldn't resist that. I thought the wheel coming off was a nice touch. All right, let's go to Mars. I'm going to start with the Spirit rover. This is the landing site for the rover Spirit. We landed inside this crater here. It's named Gusev crater. It's 160 kilometers, about 100 miles in diameter. It is at 16 degrees south latitude in the southern highlands of Mars. The reason we chose it is this. There's a great big dry riverbed flowing into that crater. Now, there's no water in that river now. There hasn't been for billions of years. But this is a big hole in the ground with a dry river flowing into it. There has to have been a lake in that river in that crater once upon a time. So we went to Gusev crater with the hope of finding ancient layered sedimentary rocks that had been deposited billions of years ago in a Martian lake. We landed and we saw this, nice and smooth and flat. I managed to convince myself for about 2 days that this is what a Martian dry lake bed should look like. But then we started to look at the rocks in detail. The first rock that we ever looked at with either one of these rovers was this one here. We named it Adirondack. It's about this tall. And we hit this thing with everything we had. We looked at it with our cameras, our spectrometers, our microscope. We put a hole in it with a rock abrasion tool, looked in the hole. I mean, do you see any layers? Okay, there's nothing. This is not a sedimentary rock at all. What we discovered is that this is a piece of lava. It's a volcanic rock, and every other rock around it is a piece of lava as well. It's basaltic lava, one of the most common rock types on Earth. Mars faked this out. I still believe that those layered sediments are down there somewhere, but what happened here was after the lake dried up, after the sediments were deposited, everything got covered with lava. And we didn't know that until we got down on the surface. And it was, at the time, a bitter disappointment. Now, our vehicles, as I said, were designed to last for 90 days and designed to drive 600 meters over their lifetimes. At the point where we landed, when we looked around, we discovered that off to the southeast, there was a beautiful range of hills that we named the Columbia Hills. We named them after the Columbia Space Shuttle. And there are 7 summits in the range, and we named each of them after one of the Columbia astronauts. The Columbia Hills were 2.5 kilometers away from where we touched down. And initially, they seemed impossibly distant. Fortunately, the rover held up pretty well. And once we realized what we had landed on, we decided we should head for the Columbia Hills, and we reached the base of the Columbia Hills on day 156 of our 90-day mission. And this is the hill that we first reached, and the one that we chose to climb. It's named Husband Hill. It's named after Rig Husband, who was the commander of the Columbia when it went down. We began to climb Husband Hill, and now we started to see some rocks that were very, very different from what we had seen before. This is a picture taken with our microscopic imager. It is only 3 centimeters, about 1 inch across. And now what you're seeing is fine layering within the rock. That's something we hadn't seen before. When we look carefully, this is a rock called lutefisk. And when we look carefully at the rock, what we found is that the rock is composed of grains, but they're all different sizes. If you look at this rock through the microscope, you can see that there's some little tiny grains way down at the limit of resolution, others that are millimeters in size. When you see a rock that's made of grains of very different sizes all jumbled up together like that, it speaks of a violent process involved in its origin. If you have gently flowing water, gently blowing wind, there's some grain size that tends to be most efficiently transported, and all the rock will be composed of grains about the same size. But if something goes boom, if there's some big explosion, some violent event, it's going to put fine grains, coarse grains, everything, dump it all out together. And so when you see a rock like this, it means that something violent happened here. We also began to see evidence of water. This is data from one of our spectrometers. You can see the dots. These are the data points. The colorful curves here show you the minerals that are present. And the interesting and important one is this blue one here. That's a mineral called goethite. Goethite is an iron oxyhydroxide. Its chemical formula is FeOOH. OH. You need water to make this mineral. And so by finding goethite in the rocks, we know that water was involved in the formation of these rocks. What we think these rocks are ejecta from impact craters. Violent event takes place, throws a bunch of rock up in the air all at once, falls out in layers, and then if there's water present, you can alter that and make minerals like goethite. We climbed, first ever mountaineer on Mars, over nearly 600 days up to the very summit of Husband Hill. And you can get a sense of scale from the Statue of Liberty there, how high this mountain was. As any good mountaineer does, when we got to the top, we took a picture. This is a picture looking off to the south. And as we speak right now, the Spirit rover is perched right there on the edge of this very bright plateau of layered rocks that's a feature that we've named home plate. This shows the path that we followed as we came down off the summit, drove down here, eventually got to home plate right there. When we got to home plate, we discovered that it too was a consequence of an explosive event, in this case a volcanic explosion. What this has is a feature in here that a geologist would call a bomb sag. To a volcanologist, a bomb is a rock that gets thrown up in the air by a volcano and then falls down and could land on your head. Okay? And what happens is when a volcanic bomb lands in soft volcanic ash, those ash deposits can sag beneath the bomb that it comes and impacts, and you get a feature like that called a bomb sag. So this is an explosive volcanic deposit. Right next to home plate is a little valley. And as we were driving through that valley about a year ago, we made an extraordinary discovery. Now, I should preface this one by saying that Spirit has had a tough time, and pieces of that rover are starting to break. The right front wheel on Spirit will not turn anymore. And so when we drive Spirit, we have to drive it backwards. And we drag that dead wheel as we drive. And it makes it really hard to drive. But the silver lining to this is that as we drive and as we drag our dead wheel, it digs this wonderful hundreds of meters long trench through the Martian soil. And every now and then, something interesting pops up in that trench. We were driving through this valley one day, and the trench that was dug by the wheel popped up with soil that was bright white as new snow. We looked at it with our infrared spectrometer, and what we saw was this big W shape right here in the spectrum. That is the spectral signature of amorphous silica. Not quartz, but opal. So big W here stands for, wow, look at all the silica. We went in and looked at it with our X-ray spectrometer. This stuff is 91% pure SiO2. This is the kind of thing that you find in a hot spring deposit. So we found this in the soil. We also wanted to look for it in the rocks. We looked at it with our spectrometer, and we saw rocks that looked like they were rich in silica. But the problem is we didn't know if we were seeing rocks that were rich in silica all the way through, or if it was just the silica coating on the outside. So we decided we needed to break some rocks. This was something that the rat couldn't do. We needed something a little more violent to make this work. So what we decided was to just try to crush some of these rocks with the rover wheels. Blunt force trauma in the service of science. And what we did, we picked some rocks here, went over with the wheels, went back again. The rocks did not break. However, right next to it were some rocks that we weren't aiming for that did break. And that rock gained the name Innocent Bystander. This is Innocent Bystander right here. And Innocent Bystander not only broke, but it obligingly flipped itself upside down, presenting a fresh broken surface, which we were able to measure, and it was chock full of silica. So this is silica rich through and through. What we believe we have found here is evidence for an ancient hydrothermal system on Mars, a place where there were ancient hot springs. Okay, what happens is hot water circulates beneath the ground. Silica is highly soluble in water at high temperatures. It dissolves silica out of the rock. It comes up to the surface. The water cools off. It deposits the silica. If you go to Yellowstone and you look at the pretty white rocks around the geysers, that's amorphous silica. That's the stuff that we're seeing here. The interesting thing is that you can go to hydrothermal deposits and hydrothermal systems on Earth, and they are teeming with microbial life. Now, I don't know if anything was living here, but if I could go to one place on Mars, pick up one rock and stick it in my pocket and bring it home, I think innocent bystander is probably the one that I would choose. Spirits had a tough time through all of this. We've had a lot of problems with dust. There is dust in the Martian atmosphere, and it falls from the sky, and it coats everything, including the rover solar panels. This is a self-portrait. This is a picture that Spirit took of itself on day 330 of the mission. And the solar arrays are brown. They become coated with dust. What happens is the dust falls out of the sky, coats the solar arrays. When these vehicles were brand new, straight off the showroom floor, 900 watt-hours of power was what those solar arrays would produce. That's enough electricity to run a 100-watt light bulb for 9 hours. The power went down and down and down as the solar arrays got coated with dust. And at the time this picture was taken, they were putting out about 300 watt-hours of power. And we think that death is somewhere around 200 watt-hours. So this vehicle was close to the end. Then one glorious day, this happened. A lucky gust of wind hit the vehicle, cleaned it off, and the power jumped back up to 850 watt-hours. Pure dumb luck. It was as if this had happened. Somebody just sent me this picture the other day. I thought it was funny. We had hit the windy season on Mars. Check this out. Dust devils. Little Martian mini tornadoes that we see whirling across the scene in the summertime. I'll play this again. I love this video. You can almost see Dorothy and Toto flying through the scene. Check this out. What was that? What was that? Eclipse. Very good. An eclipse. That's right. Mars has two moons. Their names are Phobos and Deimos. They're little tiny things. This is the moon Phobos passing in front of the sun. This is the first solar eclipse ever witnessed from the surface of another planet. There's no science in this at all. We just did it because we could. I'll give you a little more astronomy since this is an astronomy lecture. Here's a lunar eclipse. There's Phobos disappearing into the shadow of Mars. I'll watch it one more time. There it goes. We were able to observe Phobos directly. Here's a nice picture of it. Shows a little crater there. The crater's name is Stickney. This is what it looks like if you look at it with a spacecraft. We found a meteor. This surprised us. We were taking a picture of the sky one night, and there was this streak across the sky. That kind of got our attention. We initially thought it might be a spacecraft. There are a lot of spacecraft in orbit around Mars. We managed to convince ourselves that maybe this was the old derelict Viking 2 orbiter. Then what happened was a research group in France calculated when and where meteor showers should occur on Mars, when they should occur and where they should be in the sky. And it turns out it matched the timing and the orientation of this just perfectly. So we think this is a Martian meteor. And just so there's some real astronomy here, this is the one bit of extragalactic astronomy that we ever did. That is the Large Magellanic Cloud as viewed by our PanCam cameras looking up at the sky on Mars on a very clear night. And that's a sunset. On Mars, there's so much red dust in the atmosphere that the sky is pink in the daytime, but it turns blue at sunset. It's the opposite of Earth. Okay, let me go on to the rover Opportunity. We chose the landing site for Opportunity not because of its topography. No big hole in the ground, no dry river flowing into it. We chose it because of its chemistry, because of what the rocks are made of. This is data from an infrared spectrometer in orbit around Mars. The blue is boring old lava again. But the red and yellow and green up here, that's a mineral called hematite. Hematite's an iron oxide. It is a mineral that is sometimes found in rust. And it is a mineral that often forms as a consequence of the action of liquid water. So this is like a chemical beacon visible from space saying water may once have been here. It's a shame this got cut off over here. But you'll be able to see it anyway. These are some of my favorite pictures from the entire mission. Our lander had mounted on it, looking downwards, a camera that snapped 3 pictures as the vehicle is falling towards the surface. These 3 pictures are shown here. That black dot, that's the shadow of the parachute. Okay? So here it is viewed from overhead. Here it is viewed obliquely. The red curve shows the reconstructed trajectory that our vehicle followed as it went through the landing process. So we're coming screaming in from space, going 200, 300 miles an hour. Right here, right here. We inflate the airbags, cut them free, let them fall to the surface. They fall to the surface, and they start to bounce. The wind, which that afternoon was blowing from the south, causes the trajectory to bend to the north, bounce, 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 bounce. And then reading the green perfectly, the trajectory bends to the left and goes right into a little 20-meter diameter impact crater. Tiger Woods on his best day could not have pulled off this landing. We opened our eyes, and there was a spectacular outcrop of layered bedrock right in front of the rover. Now, the night that this happened, the night that we landed, we didn't know where we were. We didn't know what crater we had rolled into. We didn't know how big it was. We didn't know how far away the crater wall was. We didn't know how big the outcrop was. And when we first saw this, my team named this giant outcrop that we were going to have to deal with. They named it the Great Wall. That was the name that they gave it. Then we took some stereo pictures, did a little math. Little tiny outcrop, great big rover. The thing was this big. Okay? But its small size was part of its charm, because what that meant was the very fine layering that we were seeing was indeed extraordinarily fine. This wasn't lava. This was something different. We went looking for the hematite right away with our infrared spectrometer. We found it right away. This is a hematite map. Red is lots of hematite. Blue is none. There's lots of hematite on the plains outside the crater. There is a bit of hematite in the outcrop, not a whole lot. And then on the crater floor, there are these splotches with no hematite. The splotches are airbag bounce marks. You bounce in the dirt here, and hematite goes away. That was the first of many puzzles. Here, I've shown you this before. This shows the bounce marks. Bounce marks are very smooth, no hematite there. In between the bounce marks, lots of gravel. So now we're thinking, well, maybe the hematite's in the gravel. And you bounce on the gravel, and it pushes it down into the sand, and it disappears or something. We drove off the lander, and we looked down, and we took this picture of the gravel, and we started to notice that some of those grains of gravel looked awfully round. So we whipped out our microscope, and we took this picture. And I will remember as long as I live where I was standing and how I felt and the unrepeatable words that I said when I saw this picture. The surface of Mars at this place is littered with an uncountable number of little round things. And they're 4, 5, 6 millimeters in diameter, and they are absolutely everywhere. We had not a clue what they were. So having been baffled by that, we drove over to the outcrop, and what we found there was that the little round things are embedded in the outcrop like blueberries in a muffin. And the blueberries are hard, and the muffin is soft, and the muffin erodes away, and the blueberries fall out. And they're everywhere. Now, by this time, of course, we were desperate to know what the blueberries were made of. We suspected that they were made of hematite, but we didn't know for sure. This is a microscopic imager picture, shows one of the little blueberries in the layered muffin rock. And we had a really nice spectrometer on the end of our arm that was a great hematite detector. The problem is that the field of view of that thing is pretty big. It's 1.5 centimeters across, and the blueberries are much smaller. So if you go and you try to isolate a single blueberry with a field of view that's that big, what you get in your field of view is a little bit of blueberry and a whole lot of muffin, and it's hard to tell what you're looking at. So what we needed instead was a gathering of blueberries. And we found one. There was this place where there was a little bowl-shaped depression in the rock. We called it the berry bowl. And a bunch of berries had rolled down into it. And we stuffed our spectrometer inside, and what we saw was this spectacular multi-peak spectrum. That's hematite. What we came to realize is that the blueberries are what geologists call concretions. Concretions form in sedimentary rocks on Earth that are saturated with water. And dissolved in that water is some mineral like hematite that wants to precipitate out. It finds a nucleation point and begins to precipitate. And what happens is it starts to grow. And it grows and it grows and it grows. And it adds layer upon layer upon layer, making this hard spherical mass, like the way an oyster builds a pearl. And so what this is telling us is that these rocks were saturated with water at some point in the past. Now, we were also interested in knowing whether or not water had ever come to the surface. If you have ever looked into the bed of a sandy stream, you have seen this. When water flows over sand, it makes ripples. And the ripples move downstream. And the key here, this is only 40 centimeters across. The key here is that the ripples have highly sinuous crests. These are not nice straight ripples. They have very sinuous crest lines. And that high sinuosity is the signature of water as the fluid that is making this stuff move. Here's the same thing being simulated in a computer. Sinuous ripples moving downstream. And now look what's left behind in the geologic record. It's not nice, straight, flat, parallel layers. Instead, you get these concave upward, these smiley shapes in the rocks that are the signature of those propagating ripples. Here's the real thing from some sediments in the Colorado River in the southwestern United States. Little smiley shapes within the sediments. Here it is on Mars. Little smiles, 5 centimeters, 8 centimeters across, running through the rocks, telling us that at this place, water flowed over the surface. Here's a favorite example of mine. This is a rock called Cornville. You can see the little smiley shapes all through it. Here's a rock on Earth that has those same features. This is a very old rock on Earth with ancient ripple marks. And here's the same thing on Mars at the exact same scale. So water flowed across the surface here, at least occasionally. We spent 60 wonderful Martian days exploring a crater about the size of this room. We named it Eagle Crater. We made kind of a mess of the place, actually. There are wheel tracks everywhere. And then we left Eagle Crater with the intention of going to another crater that we had named Endurance Crater. Bigger, better, deeper. It was 150 meters in diameter, about 20 meters deep. I remember going to press conferences and saying, boy, we're going to get to Endurance Crater, and we're going to discover new stuff. It's going to be much better. We got there, and it was terrifying. I mean, this thing looks like an overhanging cliff. It is. This is the kind of place where if we screwed up, a little rover could fall off a cliff and die. But look at those layered sedimentary rocks. We had to find a way to get there. Now, I showed you that picture before with the little tiny outcrop and the great big rover. Here it is at Endurance Crater. It's a scary place. But in 10 months of operations, we drove that little rover down into the crater and up to this spot right here. The wheels were straddling that rock, and I will show you a picture taken from that spot in just a moment. Now, when we got to Endurance Crater, we had no idea how good a climber this rover was. We didn't know if it could handle this kind of terrain. We had to test it. So we went out to Home Depot, literally, and we bought a bunch of rocks, a bunch of sand. I had grad students gluing BBs onto the rock to make blueberries. And we took our test rover and we ran it up and down the slope, and it worked pretty well. So in we went. Over a period of months, we worked our way methodically down this wonderful stack of layered rocks. Each time we got to a new layer, we would put in a hole with our rock abrasion tool. We would take pictures with a microscope, measure the chemistry, measure the mineralogy, do a vertical section through the rock, what geologists call a stratigraphic section. It's the first stratigraphic section ever done on another planet. Things changed as we got deeper into the rock. Up near the surface, you could see the layering in the rock preserved well. Once we got deeper down, the rock was lumpy. It was irregular in its texture. It has the kind of texture that you have when rock recrystallizes. These rocks, as it turns out, are made largely of salt, sulfate salts that were deposited when water evaporates away. And when you soak that kind of stuff in liquid water, you can recrystallize it. In fact, you can dissolve things away. This rock here had lots of magnesium sulfate in it. This rock here had a lot less. That magnesium sulfate had been completely dissolved away, again, by the action of water. There was some weird-looking stuff down inside the crater. This was a rock down inside the crater that when we first discovered it, my team named it the petrified Martian dinosaur brain. When this picture came down, one of the guys on the team said, now that's what a rock from another planet should look like. No idea what's going on there. We drove to the bottom of the crater, and then we drove up to the base of that cliff that I showed you. We took this picture right here. I wish that I could show you this picture in all of its high-resolution glory. There's about 3 IMAX screens worth of data in that image. I can't show that on this screen. I'll just blow up one little section right there. There it is at full resolution. The whole image is that good. All of this is on the web. All of you, researchers anywhere, can download this stuff, do science with it. I think this is going to be keeping planetary geologists busy for a few decades. We finished up an endurance crater, climbed back out onto the plains, and the next place that we went was our heat shield. Remember the heat shield? It protects the vehicle as it falls down through the atmosphere. It comes off of the vehicle by design during the landing process, free falls to the surface, and crashes onto the ground at about 200 miles an hour. Here's what it looked like the last time I saw it in Florida. And then here it is in pieces on the Martian surface and the crater that it made when it hit. Now, we went to the heat shield not to learn about Mars, but to learn about heat shields. Okay? For decades, people have been trying to land on Mars. And for decades, engineers have been given the task of trying to design a heat shield that will work in the Martian atmosphere. But until our mission, not one of those engineers had actually had the luxury of seeing their creation after it had done its job. We were able to drive right up to the heat shield, take out our microscope, take a cross-sectional image through it right here, and hand that image to the engineer who had designed and built the heat shield so that he could assess how well it had performed. Now, at the same time that we were doing our investigation on the heat shield, we're looking around for rocks, right? Because we're geologists, we're looking for rocks. We found this one. It was sitting right next to the heat shield. We called it heat shield rock. We went over to it. We measured its spectrum. And it turns out that that rock is not made of rock at all. It's made of a nickel-iron alloy. It's an iron meteorite. This is a big honkin' iron meteorite just sitting there right next to the heat shield. Again, pure dumb luck. I told the team we shouldn't stay here. This is obviously the place where big metal objects fall from the sky. We left the heat shield and we drove south for many kilometers. And as we got farther and farther to the south, we began to encounter these ripples. And the farther south we got, the bigger they got. And they got larger and larger and larger until they were kind of dune-sized. And we were driving along one day using a driving technique that I think could be charitably described as bombing along at top speed with our eyes closed. And we got to one of these dunes, and I still don't know what was different about this dune from all the others, but somehow we got stuck in this one. We broke through, and we did 50 meters worth of wheel turns, thinking we were driving happily across the plains of Meridiani, when in fact we were just digging our way down deeper and deeper and deeper and deeper. And we came in the next morning, and all 6 wheels were buried over the hubcaps. Now, the first rule in a situation like this is don't do anything stupid that's going to make the problem worse. Take your time, work it out. The vehicle was safe. It sure wasn't going anywhere. So we had time to work the problem. Now, in order to work this problem, what we had to do was to simulate the predicament that we had gotten ourselves into on Mars. We actually built 4 rovers. 2 of them are on Mars. 2 of them are back here on Earth. This is one of them, and we use it routinely to simulate situations we've gotten into on Mars. Now, in order to simulate this particular predicament, what we needed was really good fake Martian soil. If you're ever called upon to make fake Martian soil, here is the recipe that you should use. It's equal parts play sand, the stuff that you use in kids' sandboxes, clay, and diatomaceous earth, the stuff that you use in swimming pool filters. Once we worked out this recipe, a bunch of engineers in pickup trucks went fanning out across the LA basin and bought up literally tons of these 3 ingredients. People were getting algae in their swimming pools across Los Angeles all summer long because of us. We brought it back to JPL, mixed it all up, and we made pits and mounds and dunes, and we would drive our rover into it and get it stuck. And then we spent 2.5 weeks rehearsing, trying to find the optimal technique for extracting a robot from a sand dune on another planet. And there are a lot of things you can do. You can steer the wheels back and forth to open up the holes. You can drive the wheels at different velocities. You can rock the vehicle. Okay, we tried all of those things. After 2.5 weeks, we found the optimal technique. The optimal technique, it turns out, was to put it in reverse and gun it. There's no place you go to look this up. Okay, so here we are gunning it. And it was awful. I mean, we had to do 192 meters worth of wheel turns to get the rover to go 1 meter. I mean, that's the left rear wheel. I mean, look, we were stuck. It was really bad. And then one glorious Saturday morning, after 6 weeks of this, the rover popped back out again of a feature we have later come to call Purgatory Dune. And we have been treating those dunes with much greater respect ever since. This gives you a sense of scale. Again, there's stuff sort of missing here. But here's the Eagle Crater where we landed, Endurance Crater where we spent so much time. Drove across the terrain. Purgatory was right about here. Erebus Crater. Our goal was to reach this crater here, which we named Victoria Crater. All of the craters at this landing site were named after famous ships of exploration. The Eagle was the Apollo 11 lunar module. Endurance, of course, was Shackleton's ship. Victoria was one of Magellan's ships. Magellan left Spain with 260 men on 5 ships. The Victoria was one of them, with the intention of being the first to completely circumnavigate the globe. Magellan himself was killed in the Philippines. After 3 years at sea, the one surviving ship, the Victoria, with 18 surviving sailors from the original 260, limped back to Spain. We chose that name for this crater because we thought it would be an appropriate analogy for the condition that our poor little beat-up rover, driven by 18 surviving graduate students, would be in if we ever made it that far. I'm pleased to be able to report, however, that we did make it. Not only did we get to Victoria Crater, but just coincidentally, again, good luck, just at the time that we pulled up to the rim of Victoria, a new NASA orbiter called the Mars Reconnaissance Orbiter eased into orbit around Mars, turned on its camera, and took this spectacular picture of Victoria Crater. I will blow up just this portion of it. And if you look carefully, there's the Opportunity rover. And in fact, you can even see, if you look very carefully, the shadow of the camera mast being cast on the Martian surface. It was really nice to see our rover again. We spent almost a year driving along the rim of the crater. You can see the wheel tracks that we made as we drove along the crater rim and back. The rover drivers told me when this was all done that was going to spell out, "Hi, Steve," and I'm not seeing it. But we drove out to the tips of those promontories, and we would take images of some of the cliffs that we saw. This is one that we named Cape Verde. I'll blow up just a portion of it. And this is very typical of what we see along the rim of the crater. Down here, we have more or less intact bedrock. Then we have bedrock that's fractured but still in place. And then above here, there's just a jumble of rocks. That's the stuff that was thrown out of the crater. Okay, so if you had had the misfortune to be standing at Meridiani Planum the day the Victoria Crater is formed, your boots would have been on this surface right here, right before a whole lot of rock fell on your head. What happened, what we're seeing here, this is what a cross-section looks like through a typical impact crater right after it's formed. If that crater erodes, the rim erodes away and the floor of the crater gets filled in, you get a configuration like this. And in fact, that's what we're seeing right there with our little rover on the rim of the crater. We also see just exquisite layering exposed in the bedrock itself. This is a place called Cape St. Mary. I'll blow up this portion of it right here. And look at that. Just spectacular layering exposed within the rocks. If you took this picture and you showed it to a geologist on Earth and you said that this was from the Navajo sandstone in in Zion National Park in the United States, they would probably believe you. Now, I don't know if you've been to too many talks by geologists, but one thing that geologists always do when they take a picture of an outcrop is they put their rock hammer in the scene for scale. So there's my virtual rock hammer to give you a sense of scale. I wish it were my real rock hammer. As we speak right now, the Opportunity rover is right there at a place called Duck Bay, down inside Victoria Crater. We've worked our way again down this wonderful stack of layered rocks. We're here right now, and we're trying to get to this cliff here. That's the other side of Cape Verde. About 3 or 4 hours ago, this picture came down. So this is what it looked like on Mars earlier today. This is looking out the front end of the vehicle. There's Cape Verde there. This is some very treacherous terrain here. It's slippery. It's dangerous. I don't know if we're going to be able to cross it or not. We're going to give it a try, and we'll see what happens. Whenever I give talks about this project, I always end them with this slide here. I wrote a book about the project called Roving Mars, and in an appendix of that book, I made an attempt to list the names of all of the people who worked on the project. There are more than 4,000 names on that list. I'm just one part of this team. This is a bunch more of the team. This is a Cape Canaveral. That's Opportunity in the background. This is the night that we sent Opportunity out to the launch pad. For every one of us who has had the remarkable experience of being part of this mission, it has been, in the very literal sense of the phrase, the adventure of a lifetime. And I really want to thank you very much for inviting me here to tell you about it. Thanks a lot. Thank you.
Steve got up at 3 o'clock this morning. I think he's shown you the depth of his commitment to telling the story of science and exploration, and both in his being here and the wonderful way in which he has done it, and we really appreciate that. There's time for a few questions if you'd like to ask some.
Sure, fire away. Right here.
Have there been any spectra you haven't been able to understand, types of rocks that you haven't been able to identify?
Have there been any spectra that we have not been able to understand? Yes, but I think that is more a shortcoming of our instrumentation and our analytical abilities than the indication that there's something mysterious on Mars. That was bright. There have been a few things that have turned up in some of our infrared spectra that we've had a hard time pinning down exactly what they are. I don't think that that's an indicator that there's some mysterious Martian mineral that no one's ever seen before. I think it's just more likely that that our spectrometer is not able to disentangle some of the complexities of a number of different minerals mixed together. So nothing that I would attribute to being anything particularly mysterious. Yeah.
Incidents, I guess, more severe than being stuck in the Dune?
Oh, more incidents. More severe than that. Actually, I think the most serious trouble either rover ever got into was when we had a global dust storm. Mars occasionally undergoes global dust storms, and we had one that just blacked out the skies. I mean, we literally, you couldn't see where the sun was. We have cameras that can look up and look for the sun, and it was so bad that you couldn't even see the sun. And for a solar-powered rover, that's a bad situation. Opportunity nearly died. I think if that storm had gone on for maybe another week, we might have lost that vehicle. It was that bad. So that was probably the worst situation that we've gotten into. And the thing that was awful about that was there was kind of nothing you could do. I mean, you were just sitting there watching Mars trying to kill your rovers, and there were little things that we could do to try to, use power very, very efficiently and try to harbor them and keep them safe as we could. But that was just a terrifying thing to watch. And fortunately, the storm abated and it was okay. But that was a real close one. And we've had a bunch of other things as well. But those are a couple examples. Yeah.
This has been extraordinarily successful on the decisions that you're making as to where to go, what to do.
Right.
Becoming, on the one hand, more adventuresome or more reckless. And this is all tied up with the fact, what's going to happen? Do you envision a natural death?
Oh, in a lot of ways these could die. I wouldn't say, well, okay, we are doing things with the rovers today that we would not have dreamed of earlier. But we have not gotten more reckless. We've gotten better at our jobs. So I think we're actually taking maybe less risk today than we were early on. Certainly not more. I think we've become, there were risks that we took early on that we didn't know we were taking. That business with the sand dune, we thought we were doing was safe. We didn't think we were taking a risk. We thought these sand dunes were safe. We had driven over dozens of them. Nothing bad had happened. And then we realized, oh, no, wait, occasionally one can bite you. So we've gotten smarter. We've gotten better at our jobs. But we're still very, very cautious. We have spent $900 million of your taxpayer dollars, thank you, to get these vehicles to Mars. We take that responsibility of safeguarding these precious assets very, very seriously. With respect to how the mission could end, there are a lot of ways. One is a dust storm. That didn't quite get us, but almost did. Another is dust on the solar arrays. That could do it. We've gotten a few of these lucky wind gusts, but you don't know that that's going to happen. We could screw up and get permanently stuck in a sand dune. We could drive them off of a cliff. Okay, listen, as we were driving along the top of that cliff on the rim of Victoria Crater, I mean, we would go, wheels 20 centimeters from the lip of this 6-meter cliff. I mean, you screw that drive off, you're going to be on David Letterman's top 10 the next night. So, there are many things that could happen. I think one of the more likely scenarios, here's my favorite. Here's how I want them to end. I want to wear these things out. I want to just beat on them and beat on them and beat on them in the name of science until they just can't go anymore. I want just to run them until the motors die, the gearboxes seize up, and the vehicles we've gotten every drop of science out of them that we can. And that's what I'm hoping for. To me, that'll be the best definition of success is we wore them out. Yeah.
In the original for the Rovers, why were they not given the capabilities to search for microbial life?
To search for microbial life is really, really hard to do. Any mission that you fly, you've got to make some very tough decisions about what gets to fly and what doesn't, what kinds of instrumentation you can take with you and what types you can't. There has been one mission that did go to Mars to search for microbial life. It was the Viking mission. It flew in the 70s, and if you take the cost of Viking and you inflate it forward to today's dollars, it's about $4 billion. And that was a stationary lander, not a rover. So it's a very, very hard thing to do. It was not within our capabilities and our budget and our schedule. Yeah.
Was that an accident that you chose to land at equatorial sites?
Oh, no, it was not an accident at all. We chose equatorial sites because that's where the sun shines most brightly. Yeah, absolutely. Yeah.
I've heard you declined to be on the Mars Science Lab project due to...
Oh, not at all. I'm a on 3 instruments on the Mars Science Laboratory.
I thought that, from what I've read, that was due to having to live on Mars time.
No, not at all. No, I kind of liked Mars time, actually. Mars time, I can elaborate on the Mars time thing. Mars time, the thing about Martian time is that the Martian day is not 24 hours long. It's 24 hours and 39 minutes long. And you might think it would be nice to be able to sleep in an extra 39 minutes every day. No, it's really bad. Because what happens is, of course, if your daily operations planning meeting is at noon today, then tomorrow it's at 12:39, and the day after that it's at 1:18, and it works its way around the clock. And so, 2.5 weeks later, you're getting up in the middle of the night and going to work. We all had, well, some of us at least had Mars time watches. This is a Mars time watch. We had Mars time alarm clocks. We had blackout curtains on our windows. We had a lot of grad students, thank God. A lot of coffee. We had maid service on Mars time, food service on Mars time. It was crazy. Not only that, but of course we've got 2 rovers. And the rovers have landed at 2 different longitudes, opposite sides of the planet. So I've got to take my team of 170 scientists, divide them into 2 separate teams, one for Spirit, one for Opportunity, everybody living on Mars time, but in 2 different Martian time zones. And then if you're working on one rover and you want to switch to the other, you get Martian jet lag. So it was very confusing. The worst, what I found was that if you could just separate yourself from Earth entirely, so Earth just did not intrude into your life, then you could get into this rhythm where you slept an extra 39 minutes every day, and it was kind of okay, and it really wasn't that bad. What was problem was when Earth was when Earth would intervene. For example, there would be press conferences that I would have to attend, and for some reason they wanted to have the press conferences on Earth time instead of Mars time. And so there were, the press conferences would be 8 o'clock in the morning Pacific Daylight Time, and what would happen is I would work all day, go back to my apartment, sleep for 4 hours, set my Earth time alarm clock to wake me up in the middle of the night, Mars time, go in, do a press conference, and go back home and go to sleep. That kind of thing is bad for you. So we lived on Mars time for about 4 months, and after that, since then, we've lived on kind of a weird Earth time, Mars time hybrid, which is what we're still doing today. You mentioned MSL. MSL is planning on doing Mars time for probably about 2 months and then transitioning to Earth time.
Rover's going to be terminated if they're still running when Mars Science Lab becomes operational?
I don't think so. No, I don't think there's any reason why we would want to do that. It's separate teams, so we have the capability to do both simultaneously. Other questions? Way in the back.
History of Mars, as compared to before the rovers even.
I would say that we understand the geologic history of these two little tiny places on the surface of Mars extraordinarily better than we did before. But I am reminded of the parable of the blind man and the elephant, right? We've looked at two little spots on this very complex elephant. And in fact, the geology of Mars is extraordinarily complex, very varied from one place to another. And I think it would be a little foolhardy to assume that the things that we have learned about these two places apply globally to the planet. So I think I feel a lot smarter about the geology of two little places on Mars. Yeah? What's my bet on life? I don't have one. And I'm not trying to dodge your question. I actually mean that in a serious way. I feel that one of the most serious mistakes you can make as a scientist is to think you know what the answer to a question is in the absence of real data to support your views one way or another. Scientists have a saying that I've heard sometimes where they'll say, I wouldn't have seen it if I hadn't believed it. Okay, you don't want to fall into that trap. The problem with thinking you know what the answer ought to be, or even worse, wishing for some answer, I mean, at some level, I want to wish that there's life on Mars, okay? But if you let yourself fall into that trap, it can cause you to misinterpret your data. And so the approach that I try to take is to just maintain an open mind and go out and try to design a better experiment. So I don't have a good answer to your question.
I think on that one, we should stop. I want to commend this book to your reading, Roving Mars. Steve put together a splendid behind-the-scenes look at how all of this happens. And it's an amazing process, so I'd encourage you to get that. Steve, thank you so much.
Thank you very much.